sometimes known as vibrot. Linear diatomics. A diatomic molecule has only one degree of freedom of vibration along the bond, as shown in the diagram here. It can vibrate. This means that can move that way and that can move that way and back. The frequency of vibration is given by nu is equal to, open bracket, half 2 pi c, close, the square root of, open bracket, k over mu, close, where k is a force constant, a characteristic of the bond. Mu is the reduced mass as usual. Vibration rotational spectra continued. If we assume that the bond vibrates such that the restoring force is proportional to the displacement, that is, as a simple harmonic oscillator, then as the internuclear distance r changes, its potential energy should change along a symmetrical curve of the shape given below. Here is the curve, a parabola, where here is the normal bond length, which we are always aware of. That end is when we have greater than normal distance after stretching, and this way we have smaller than normal distance of compression. Potential energy that way, and distance of separation this way. For emission or absorption of electromagnetic radiation, open bracket IR, EV is equal to, open bracket, V plus a half, close, h nu naught, where nu is the vibrational quantum number, no, V is the vibrational quantum number, and can take on values from 0 to 1 to 2 to 3, that is integers. Nu naught is the vibrational frequency. On working out one for different V values, we obtain a series of energy levels, and they are shown here. V equals naught gives us half h nu naught. V equals 1 gives us 3/2 h nu naught, and V equals 2 gives us 5/2 h nu naught. From the same equation, it appears that when V is equal to naught, open bracket, molecule is in the ground state. That is, E is equal to half h nu naught, which means that there is a 0-point energy. For transition to occur, the quantum number V must change by unity, i.e., delta V is equal to plus or minus 1. Most molecules are in the lower energy level, ground state, at room temperature. The transition 0 to 1 on subjecting compounds is important. The band due to this transition is known as the fundamental band. Bands for 1 to 2, 2 to 3, 3 to 4 are known as the hot bands. The energy for the transition 0 to 1 is given by delta E is equal to E prime V minus E double prime V, which is equal to h nu. The frequency nu naught is known as the fundamental absorption frequency of the particular molecule. At the same time, we have a constant spacing h nu. Complications arise because rotation as well as vibration occur simultaneously, and hence we must consider the energy, including that of rotation. So EVR is equal to EV for vibration plus ER for the rotation. And we put in the equations then. This is equal to V plus a half into h nu naught plus Vj into j plus 1. And delta EVR is equal to h nu naught plus 2b j plus 1. assuming a rigid rotor and a simple harmonic oscillator, of course, in this case. The selection rules now are delta J can be plus or minus 1 and delta V can be plus or minus 1 for absorption for diatomics. Hence, vibrational transitions can occur with the increase or decrease of rotational energy. That is, vibrational energy can be subtracted from one another. Because transitions will only occur with change of rotational energy, there will not be any absorption lines at nu naught, the fundamental frequency, as there is no rotational energy at this frequency. It is important to know that. Let me repeat it. Because transitions will only occur with a change of rotational energy, there will not be any absorption lines at nu